Hi everyone. Today we are going to study transformations of cos 80, sin 80 and polynomial type. In my last video I have already updated with exponential, constant and hyperbolic functions. Details are there in the description box. So this will be the sixth transformation. So transform of cos 80. This is the next transformation we are going to study. So let the function f of t be denoted as cos 80. As we know the definition of Laplace transform of f of t is integral 0 to infinity e power minus st f of t into dt. Substitute this function to the transformation and start integrating to get the standard result. So we have let Laplace of cos 80 is equal to integral 0 to infinity e power minus st f of t into dt. So instead of f of t I am going to replace it by cos 80 into dt. So this is Laplace transform of cos 80. As we know, integration under product rule, either one should be a term which becoming constant, later on the differentiation it becomes 0. But here we have exponential and cos, both are continuous function. So we need to apply the standard integral formula, that is e power ax cos bx plus c into dx. This is a standard formula, but without the limits. Whenever you have an exponential into cos function, you can use this formula e power ax by a square plus b square into a cos bx plus c plus b sin bx plus c. So after you write this formula, make sure this formula is only for integral without the limits. So here we need with the limits. What you have to do, the entire integration of this exponential into cos has been derived. Directly take the limit from 0 to infinity. So we have Laplace transform of cos 80 is equal to e power minus st by minus s the whole square plus a square into minus s cos ax, that is 80, plus a sin 8. So here when you compare it, I'll just write it, when you compare it, exponential has instead of a it is minus s, instead of t it is x, instead of b value it is a, and instead of c value it is 0. So on careful examination you can clearly write this step. Okay. So as I told you, this is only for the integral without limits. Now we'll take from 0 to infinity. So Laplace transform of cos 80 can be written as upper limit t replaced by infinity, lower limit t replaced it by 0. So what we get, e power minus infinity by minus s the whole square become s square plus a square into minus s cos infinity plus a sin infinity, and the lower limit put t has 0. So e power 0 by s square plus a square into minus s cos 0 plus a sin 0. So we need to know e power minus infinity is 0, e power 0 is 1, Sine 0 is 0 and cos 0 is 1. So since e power infinity is 0, product of term becomes 0. E power 0 is 1, cos 0 is 1, sine 0 is 0. So we have Laplace transform of cos at is equal to, we have a negative sign, so this term is 0 first term, so it's minus of 1 by s square plus a square into minus s plus 0. So we have minus of minus plus s by s square plus a square. So therefore Laplace transform of cos at is equal to s by s square plus a square. This is a standard formula for Laplace transform of cos at. So we have the next transformation, transform of sin at. So let the function be sin at. Apply the formula, integral 0 to infinity e power minus st f of t into dt, right? So after writing the formula of Laplace transform, wherever f of t is there, replace it by the function sin at. Laplace transform of sin at is equal to 0 to infinity e power minus st sin at into dt. It is same as what we did for cos at. Exponential into sine cannot be solved by direct integration, so we are using the standard result, integral e power ax sine bx plus c into dx can be written as e to the power ax by a square plus b square into a sine bx plus c minus b cos bx plus c. This is the standard formula. Okay. So you just have to compare it. So I'll just compare here. Instead of a I have minus s, instead of b we have a, instead of t we have x, and c is 0. And we'll also write e power minus infinity is 0, e power 0 is 1, sine 0 is 0, and cos 0 is equal to 1. Since we have already derived the cos function, we will require all this data. So I'm just substituting here. Sine at becomes e power minus st by minus st whole square plus a square into minus s sine ax plus minus a cos ax. Directly take the limit from 0 to infinity. So when we apply, upper limit is minus infinity, so we have e power minus infinity by minus st whole square becomes s square a square into minus s sine infinity minus a cos infinity. This is for the upper limit, minus the lower limit e power 0 by s square plus a square into minus s sine 0 minus a cos 0. As we know this condition, e power minus infinity is 0, product of term with 0 becomes 0, e to the power 0 is 1, sine 0 is 0, cos 0 becomes 1. So Laplace transform of sin at is equal to, first term is 0 minus of 1 by s square plus a square into minus a, that is a by s square plus a square. Therefore Laplace transform of sin at is a by s square plus a square. This is a standard formula for Laplace transform of sin at. So the last transformation is the last one, eighth one, transform of t to the power n. It is like t is the variable, n is the constant. That means you are going to transform the function power constant. Okay, here I'll write variable power constant, right? So for this, again, let the function be t to the power n. So we have the Laplace transform, integral 0 to infinity e power minus st f of t into dt. So we need to carefully substitute in this formula. So Laplace transform of t power n is equal to integral 0 to infinity e power minus st t to the power n into dt. For our simplification, we are going to multiply s power n plus 1 on both the side. Okay, because direct integration is not possible, so we are making some changes so that we can apply some standard function. So s power n plus 1 Laplace transform of t power n into s power n plus 1 integral 0 to infinity e power minus st t to the power n into dt. As we know, integration is with respect to t. This will turn out to be a constant, so I can take it inside. So 0 to infinity s power n plus 1 e power minus st t power n into dt, which can be written as 0 to infinity. Base can be separated with powers e power minus st t power n into dt. So I'm just combining the powers of n together. So s power n plus 1 Laplace of t power n can be written as 0 to infinity e power minus st to the power n, because they have common power as n, and one more s I'm combining to dt. Okay. Again, this cannot be solved directly, so let us take let x is equal to st. So s power n plus 1 Laplace transform of t power n becomes 0 to infinity e power minus x to the power n into dx. As you know, when I differentiate this, dx becomes x into dt. Okay. So this is nothing but standard formula of gamma function. So from the gamma function, this can be written as gamma of n plus 1. This is a standard formula with gamma function. So from here, Laplace transform of t power n can be defined as gamma of n plus 1 by s power n plus 1. So this is a formula for Laplace transform variable power constant. Okay. Keeping this as our data, you can take a note. If n is a non-negative integer, so that means you can take n value to be positive. So in that case, we know this gamma function can be written as gamma of n plus 1 becomes n factorial. So I can replace gamma of n plus 1 by n factorial, and you can apply this formula whenever you have n has non-negative integers. Okay. So there are two formula for t to the power n. This is applied only when n is non-negative integer, and this is for negative integer as well as rational numbers also. This can be applied. Thanks for watching. Meet you in the next video. I hope the concepts are clear to everyone.